Well, thank you very much for that over-flattering introduction. Yes, I want to talk about the interplay between visual arts and mathematics, and it's had a great influence on me, that is to say, the visual arts, and I like to think visually. I've certainly, I remember when I was a graduate student, or before I was before I was an undergraduate, I thought how exciting it would be when I became an undergraduate with all those other mathematicians, because I felt, I thought differently from other people, and that I would then find people who thought like me. As a result, when I took my degree, I found there were more different ways of thinking about mathematics than I could have thought of before. So that I used to feel that if I talked to somebody, I wouldn't understand a word they were saying until finally I would get the idea at the end, and then we could continue. It's sort of like that. It's been like that ever since. So let me just try and see if I can get this working here. So that's just the title. I don't know what that is. I want to describe, to begin with, I was with a colleague of mine touring parts of Italy at one time, and I think we'd been to Pompeii and to Herculaneum, which had been completely covered with lava and excavated, and there were wonderful things there. And then we visited a villa. And the trouble is I've been trying to, just the other day, trying to find out where this was and what I saw in there. This villa had a very large swimming pool, I seem to remember, but there was no water in that. But on the other hand, there was a room, a long room, and along the wall was one of the most perfect examples of perspective that I'd ever seen. And I'd thought at that time, this was the general belief, that it took, the perspective was not discovered or thought of until the Middle Ages, much later than Greek or Roman times. And this was astounding. I just I lined my eye up with it in various ways, and the perspective was perfect. I tried to get hold of an expert on these things just the other day, and unfortunately my email went into his junk mail. And when I said, I reminded him, he said, no, your email went into the junk mail. He was surprised that my reminder hadn't gone into the junk mail. But it was only yesterday when I finally talked to him, and so we were trying to find out where this place was. And I don't know that we have it right as yet, so I can't tell you exactly where this place was or what that picture was. I was hoping you might have a photo. It was hard to take because you couldn't take the whole thing with, you'd have to have some wide-angle camera, which I didn't have, because the wall was much longer than the width of the room. So it was very hard to see, but you could go up to the picture and see these things were lined up in just the way they should be. This is just another picture. I think this one is in Pompeii, but it's a similar sort of thing. This is only a fragment anyway, so I suspect it would be nice to see the rest of this picture to see whether the perspective is as it should be. But you can see it in the middle with the lines converging as they should do in a perspective picture, and it's quite consistent with perspective rules. It's only a fragment, so I imagine it does go wider than this, but I think it gives an impression of what the middle of the picture I saw was like. But there were paths going off in different directions, balustrades and things like that, and I was able to check that the perspective was perfect. So this rather contradicted the view which I had held it up to that point, that people hadn't thought of perspective at that time. So no doubt, if the Romans had it, the Greeks presumably had it. And then when I talked to the expert, that was Yash Elsner, he said, yes, well, they certainly knew what they were doing, so that he certainly agreed with me that perspective must be much older than that. Anyway, let's move on. This is a picture where you can see the sort of perspective involved. I have to do it remotely because I don't think I want to wander over there and get lost somehow. But you'll see that the perspective looks pretty perfect and is pretty perfect. You can measure with rulers and things like that. That the converging lines really do correspond to a perspective rule. They're going off into the distance consistently with the lines lining the buildings in that way. Okay, so that's perspective, and perspective is really the origin of this kind of geometry known as projective geometry. Well, here we have another. This is an Escher. Of course, much more modern, this picture, but it really gives you some idea of perspective. I will be showing quite a lot of Eschers later on in this talk, because he does really illustrate the sort of thing that I'm trying to get at here. In fact, I'm involved with trying to write a book now with a colleague. I was trying for many years. I had the title of the book, and that's about as far I got. I have a contract. The book is called Eschermatics, and I was trying to write it by myself, and just over the last couple of years I've given up on that. And I have a colleague who we were going to write this book together, and I hope it will now come into existence within the time we've now got as our deadline. I don't know whether book writing copes with deadlines really, but that's never mind. Anyway, this is an Escher picture. We'll probably use one of this because it is a wonderful illustration of perspective. And you can see that the parallel lines of the side of the building, for example, look as though they're all converging at a single point. And that's the idea. Now I want to say a little bit more about projective geometry. In fact, here we have the sort of basics of projective geometry, which are lines and points. And you can have the geometry in the plane or in 3 dimensions or higher numbers of dimensions. But this is just in the plane for the moment. These two configurations represent 2 famous theorems. The one on the left is much older. Pappus, that's, I guess he's in ancient Greek or Roman. I'm not even quite sure where he came from originally, very old. Desargues was, in fact, part of the Renaissance. He was, came later. In fact, Desargues' theorem is much easier to prove than Pappus's theorem. In fact, you can almost see it's true directly. All you have to imagine that you have 5 planes just in general position in 3 space, and they intersect in this configuration. Then you project it down into the plane, so you look at the intersections of those 5 planes, and you can sort of imagine this thing to be a 3-dimensional thing, and that's the easiest way to prove it. You can just project it down from this 3-dimensional configuration down into the plane. Now, the Pappus theorem is much harder to prove, and I don't know how he did it originally, but it has a particular feature, and there's a story connected with this, which I want to tell you. This story is, at one point, Boston University asked me, I should say the philosophy department at Boston University in the United States, in Massachusetts, asked me to take part. Well, you see, philosophers have this idea that somebody gives a talk, and then somebody else is supposed to be the interlocutor or something, somebody who's supposed to contradict everything that the speaker had said. Something like that, anyway, to get a conversation going. And I was asked to be this respondent to a talk given by Paul Dirac, of all people. Paul Dirac. Why would I accept? I have no idea why I accepted. Completely crazy. But I did accept to do this, maybe the honor of being, talking. You see, the idea apparently came about because Dirac, who only very rarely revealed his own thought processes, had said that one of the big influences that influenced his way of thinking about quantum mechanics had been projective geometry. And these people in Boston had persuaded him to give this talk. And I thought, well, I know something about projective geometry, so maybe it won't be too bad. But the talk itself was just an elementary talk on projective geometry, without any indication of how it had influenced him in discovering his way of looking at quantum mechanics. So I think people were a bit disappointed, and that's about all I could say against his talk. So I gave a talk on twistor theory, which was something quite different. But this was my excuse to talk about twistor theory. I think it was sort of ships passing in the night, in some sense, because I learnt later what Dirac had been influenced by, and it was only much later, because somebody who'd been looking through his old notebooks had found pictures of Pappus's theorem, but where it looked as though it wasn't true. Somehow the lines bent away. I should say, what do I mean by true here? Well, you draw the figure, if you like, all except for one of the lines, and then the 3 points on that line actually, those 3 points do actually lie on a line, and that would apply to both these configurations. So you have the thing almost completed, or you could say you leave out one of the points, and then the 3 lines do meet in that point. Of course, you might have parallel lines which don't actually meet, and then you've got to do projective geometry, which means that they do meet in the projective plane. So why was Dirac interested in projective geometry? Well, apparently, according to his old notebooks, which had been looked at by this person who was looking through his notebooks, and I'm not sure, she was, I can't remember her name now, unfortunately, but she described that, and she showed me pictures. I had to give the pic back again for reasons. I wasn't allowed to copy them or anything like that. But these pictures, I could see, there was Pappus's theorem drawn as though it wasn't true. And I thought, I know what that means, because I'd been brought up on certain things about projective geometry. I knew, you see, you can do projective geometry not with ordinary, say, real numbers. That is, the real numbers measure along a line, or you can have complex numbers, or you can have other fields. And the Pappus's theorem is the condition that the field that measures your length along the line, if you like, that their field using not only the real numbers, but some generalization of real numbers, that field should be commutative. That is to say, A times B is the same as B times A. If A times B is not equal to B times A, then the Pappus theorem is not true. And so Dirac was exploring the idea. I think he just heard a talk by Heisenberg, who had explained that, distance and momentum and whatever it happens to be, energy and time, don't commute, and you have a commutation rule. P times T is not the whatever it is. One way around, E times T is not the same as T times E. And you have these commutators, and they're very basic to quantum mechanics. And so Dirac realized that this may be, at some stage, maybe it would affect the geometry of space or something like that. But he was influenced to study these non-commuting algebras. And that was very fundamental to his outlook on quantum mechanics and his famous books, his book which got reprinted several times. And this was a big influence he'd had. Anyway, it was very interesting to find this out, which was what he should have been talking about at this lecture. And it would have been very interesting to me had he done so at the time. Anyway, let's not talk about that anymore. Let me move on. Now, one of the people that I do have to talk about is Leonardo da Vinci, because he did all sorts of amazing pictures, and mostly they were mechanical devices, and you could see things with cogs and all that sort of stuff. So I just have a few of Leonardo's pictures here, and other cogs and things like that. So he was interested in machinery, certainly, very much. And here, you can see the Archimedes screw up on the left-hand side at the top. So you wind it around and it pulls water up. And so he's playing around with things like that. So it's spirals he was interested in. And here was his flying machine, which I'm sure wouldn't work. You'd have to get that thing. But you see it's got this little spiral thing at the top, which is supposed to spin round and would therefore pull the thing up. Well, I'm making just a slight comparison with a piece of mathematics here. This is a picture from one of my books illustrating a Riemann surface. I'm not going to go into mathematics in any detail when I talk about it. I'm just going to show you these things. If you know the mathematics, that's fine. But this represents how you can make, say, a logarithmic function make sense in the complex field. And it's a very important concept introduced by Riemann of how to study complex numbers by generalizing the idea of how you represent these things in terms of these surfaces which can have complicated topology. And this is the first example in a way where it winds and winds and round. I'm quite curious that you have this similarity between the helicopter that Leonardo da Vinci had introduced and this particular Riemann surface. I don't want to say too much about Riemann surfaces, but just to go on to something else. One of the things I did learn much later about Leonardo da Vinci is that he had a proof of the famous Pythagorean theorem. So you have a right-angled triangle, and the square on the two sides is equal, the sum of the areas of those two squares is equal to the area on the hypotenuse. So this famous theorem, and there is a proof given by Leonardo da Vinci, which I found a remarkable one. I'd never seen anywhere else. And the proof is given on the left-hand side in your picture, and you can see the triangle. There are two squares at the top, one big square in the middle, and then you can see the triangle sitting on top of the big square. And the thing is, what Leonardo did was you erect the rotation. Imagine rotating this whole configuration around the center of the big square, and then the triangle has another existence at the bottom. And you then draw the vertex, the right-angle vertex of those. You join the right-angle vertex of those two versions of this triangle, and you get a four-sided figure, which is the same as the one in yellow at the top. You can see it's the same because you rotate about the top right-hand vertex of the big blue square, and you rotate it round, and it becomes the other one. And if you consider the two halves of it, that shape happens twice, then you see the big square together with the two versions of the right-angled triangle is equal to the one at the top, where again is two of the same right-angled triangles, and now the two other squares. So you can see the sum of the areas of those two other squares must be equal to the area of the big square. Now, I was giving a talk about Leonardo and his relation to mathematics and things like that somewhere in Italy. And I think it was the night before I gave my talk, and I suddenly wondered about it. I wonder if this proof works in hyperbolic geometry. Now, I'll say a bit about hyperbolic geometry, but I've drawn it a little bit again on the right-hand side in this picture, as though the lines aren't quite straight. They're sort of arcs of circles and things like that. Well, that's because it's a representation of what's called hyperbolic geometry, and you can see that in a certain sense the proof still works. I should explain about hyperbolic geometry and Escher. Who's better than Escher to describe these things? Actually, let me go back to this picture. I say it does work in a certain sense, but you have to have two different notions of what a square is. If you take it's a little bit of a cheat, but it's the same proof, works just as well. It's just how do you know these things are squares? Well, you take the squares on the two top ones, and they are squares by virtue of the fact that all the sides are equal and opposite angles of, well, the particular opposite angles that you see, one of them attached to the triangle, those opposite angles are right angles. I think I have that right. So that's this definition of a square. You use a different definition of a square for the big blue one. You say that, again, all the sides are equal and all the angles are equal. So it's not quite the same definition, but if you take that curious kind of different definitions for the squares in two cases, the theorem is still true, which is quite curious. You can't do it with the definitions carrying the same for both small and big squares, but it's kind of curious that there is a version of the Pythagorean theorem which still holds in the hyperbolic geometry. Okay, well, now let's talk about these geometries. And Escher has illustrated them very nicely. You have the Euclidean plane on the top right, the sphere on the top left. Now, the point about these geometries is that they're very symmetrical. At any point, you can rotate all directions are the same, and so on and so forth. It satisfies all the Euclidean axioms except the parallel postulate. So the parallel postulate is you have a line in the plane and a point which is not on that line, then there's exactly one line which doesn't meet that line, so it's parallel to it through that point. And the hyperbolic one is the case where there's a whole slew of them, and the elliptical case, that's the top left picture, that's where they actually meet each other, so you don't have parallel lines in that sense. So the parallel postulate is violated in these other geometries, but the rest of Euclidean geometry is true. And people argued about these things endlessly for different ways. I should say that one at the bottom is what's referred to normally as the Poincaré disk. I prefer to call it the Beltrami disk, because Beltrami had it before Poincaré did, and there's no reason why he shouldn't get the credit. And he did talk about all these different representations. He knew the Poincaré disk, he knew I forget what the other one is called. They're all called other things than Beltrami for some reason. No, Beltrami had them all. It might be that Riemann had them all too, because he actually didn't write much about it, but he certainly understood these geometries. Okay, let me move on. Now I want to talk a little bit more about four-dimensional geometry and space-time geometry. And space-time geometry is not really like Euclidean because you've got a different kind of notion for the time-like directions than from the space-like ones. So we've got four axes. You've got to imagine they're all perpendicular to each other in a certain sense. There are three space dimensions. That's the normal space we know about. And then there's one time dimension as well. And Minkowski was really the one who showed how special relativity really was geometry of Euclidean geometry, but with a different signature. So you don't take the sum of the squares to make a right-angled triangle. You put a minus sign where one of them was a plus. Or, as I prefer to do it, you have three minuses and one plus. The one plus is the time, and the three minuses are the space. Some people like to do it the other way around. That's not a big point, but I prefer to do it for reasons which I won't go into here, with three minuses for the space dimensions. Okay, I just want you to get used to light cones, that's all. Now, light cones are kind of useful because you can talk about all these geometries in a different way. So here I'm imagining the future cone of a point. I should say the null cone is probably what I should call it. So they're more or less the same if you're talking about flat space. If you're talking about a curved space, then the light cone starts to do funny things. The null cone is really the thing infinitesimally at the point. So at the vertex, we have a point, and then the light rays coming out from that point. These are paths of photons, if you like, traveling with the speed of light in a straight line. And that defines this light cone. And you can slice this light cone the plane you see here, tilted over, actually slices it in hyperbolic geometry. So you can directly see. It's like cutting a sphere. If you have a sphere and you cut it in ordinary Euclidean geometry, you cut it with a plane, then you get a nice circle. Now, you see, if you take a four-dimensional sphere and you cut it with a three-dimensional plane, you get a nice spherical geometry. Now, if you take it with this thing, you get hyperbolic geometry. So it's a nice way of representing hyperbolic geometry. I don't want to say too much about that here, but it's a way of doing it. And here's another way of doing it, where you have all the three geometries there. I'd like to show these pictures because I drew them for my book, and so I'd like to show off the pictures because they're quite hard to draw, and I was quite proud of this one. And you see here we have a line which just touches the cone. We've got the light cone again, a null cone, the light cone, and you've got a line which is just touching it, and then three planes through that line, and depending on how they are in relation to the cone, you get all three geometries. So if it's sort of parallel to the opposite generator of the cone, then you get the Euclidean space. If it's pointing upwards, then you get the hyperbolic one. If it's lower down than the original one, then it's an elliptic space or geometry of a sphere. So you get them all in the same picture. So I rather like that. Okay. This I'll just show you briefly. You have to think in 4 dimensions for this picture properly. The picture on the left is meant to be a sphere in 4 dimensions. So it's a 3-dimensional hypersurface in a 4-dimensional space. And this is a really rather remarkable structure. It's what describes what's called a fiber bundle or a fibration. You see, there was a thing discovered by Clifford. It became later known after the person Hopf. Well, Hopf discovered a lot of other things. I think he gave Clifford credit, but this is actually what's referred to as the Hopf vibration, but it's really Clifford originally. But you see the 3-dimensional sphere is in the box thing at the left, and then we have lots of circles drawn on that, which fill the whole space up. And these circles all link each other. That's the Hopf vibration, or the Clifford parallels, as they're called. And on the right-hand side, I've imagined those circles, and you have the picture on the right-hand side is describing the idea of a fiber bundle. So you've got these circles, and you've got a sphere's worth of them. So what it means is you've got a sphere's worth of circles, but they're not just sort of stacked up parallel to each other in a certain sense. They're stacked up in a more complicated way. They link through each other, and that gives you the 3-sphere. So the 3-sphere is a 2 spheres worth of circles. And this picture is supposed to be illustrating that. This was very important to me for something I did later. And here I've tried to draw a picture of the Clifford parallels, or the Hopf map. This is what I call a picture of a twister of a sort. I'm not going to say anything more about twisters except that this picture is why they're called twisters. I was trying to find a generalization of the idea of a light ray for a reason which I won't go into, which added just one more dimension. And it really represents, you see, a photon has a certain spin to it. And you can think of this classically as well as quantum mechanically. But the photon spin has a curious characteristic to it. And it's as though when you move off sort of into the complex in a certain way, you get this structure. So it's the way in which as you go around, you see how the spin with respect to the photon, how does the angular momentum of that photon, how does it move, how does it behave as you go around at different places. So you should imagine the photon is zipping along in the direction up to the top right, where that particular thick arrow is pointing. That's the photon zipping along that, carrying along the structure as it goes, and this structure tells you what the angular momentum of that photon looks like. It's not a picture people are usually familiar with, even if they work with these things in physics, but I like to play with these things geometrically. And the space of these things is what I call twistor space. I can't remember whether I've got any other pictures about twistor space, but I thought I would tell you where the name comes from, because these things do indeed twist around each other in this way that Clifford parallels do. Okay, well, now I'm going back to this hyperbolic plane, and this is another of Escher's pictures. This is actually the first one that he drew. He drew, I think, 4 of them called circle limits, and they all very, very beautifully illustrate the hyperbolic geometry. I think I saw the original of this picture once I think there's an exhibition in Edinburgh or something, and I went there, and I looked at it extremely closely, and you can see how these fish creatures get very, very tiny right up near the edge. And it's remarkable how Escher really painted them right up to the edge, very, very precisely. It's because he couldn't do it ad infinitum, but he did it much more perfectly than you can see in this reproduction here. So he was really extraordinarily skilled in these things. How he knew exactly what to do is very remarkable. He learned about this hyperbolic geometry from the great geometer Coxeter, who was a Canadian, and I think he spent a lot of time in England, but he had visited, when I was in my second year as a graduate student in Cambridge, I think it was, and the International Congress of Mathematicians was being held in Amsterdam, and I, with a colleague, went to this International Congress, and I remember hearing lectures which I didn't understand. Hermann Weyl, I remember not. Oh, Sayre, I don't think I understood anything he was saying, but it was a nice education nevertheless. But I was getting on a bus, and then one of my topology lecturers, this was Sean Wiley, and he was holding this catalogue, and he said, I said, what on earth is that? And he said, oh, you should go and see this exhibition due to the work of M.C. Escher. I'd never heard of him. And Coxeter, who'd also been at this exhibition, told Escher about this Beltrami representation of the hyperbolic plane, and Escher picked up on it, and there are these 4 beautifully done. This is very nice if you want to talk about the mathematics, because you can see as you follow, say, the black fish, and you follow from nose to tail as you go right round, and you get arcs of circles which meet the boundary at right angles, and those are the straight lines of that geometry. It's a conformal geometry, and you can see what does that mean. Well, small shapes are preserved even though the sizes aren't accurately represented. And you can see this nicely because the eyes of the fish are exact circles, and they remain circles no matter how close to the edge you get. So it preserves the circularity and more generally the shapes of small figures, even though the size can be different. So this is an important thing to remember, that you can have this kind of geometry, and it's a very, I think, sort of parallels the idea of projective geometry. You see, projective geometry in the plane, you've got infinity is represented by a line, as I think I said before. You've got a vanishing point which might be out if you actually do get parallel lines and relative infinity. So you have to imagine there, in the plane, there is another line sitting out, or in 3 dimensions, it's another plane sitting out as infinity. Whereas in the conformal geometry, what sits out as infinity is a point. So you get a point which folds the sphere. Sorry, I should say it's a point if it's a positive curvature. No, I've said it wrong. It's a point if it's the Euclidean plane. What's at infinity? It's a point. But if you have a hyperbolic geometry, what's at infinity? Well, it's a circle if it's 2-dimensional, or a sphere if it's 3-dimensional. And you have to get used to those ideas, and it's very helpful to think of infinity as somewhere nice that you might go and visit someday. So it's a kind of a useful picture, I found. I've just shown this picture. It just shows the lengths to which Escher would go to illustrate the idea, in this case, of 2 intersecting tetrahedra. These are regular tetrahedra, and this is a very nice, he played with this intersection quite a lot, but this one is, he imagines these are 2 interlocking planets, and one is all the bad guys on one planet and all the good guys on the other planet. I suppose dinosaurs are meant to be bad guys. I'm not sure if he characterized them that way. I don't think he did. But you can see one of them's got prehistoric creatures on it and the other one's got civilized things going on. I always liked that picture. Let's move on. Well, here we have a picture with a bit of personal history involved, which I suppose I should go into. Yes, I'm not quite sure how I should express this. Let me go back. It doesn't come yet. Sorry, it's not backing up the way I expect it to. Oh, that backs up. Yes, that's it. Okay. Now, this picture was... I'll tell you the story first, and illustrate it a bit later, because I think I've got it not in the order I meant to. I'd been to see this Escher exhibition. You see, Sean Wiley had shown me this catalogue and said, oh, you must go and see this. I'd never heard of Escher before. And there was this wonderful room in the Van Gogh Museum, which was devoted to Escher's pictures, right round the room with these extraordinary things. I'd never seen anything like them before. I know that one of the things that impressed me most, a thing called relativity, where gravity was in 3 different directions and all that kind of thing. And then I came away thinking, I'd like to do something impossible myself that I hadn't quite seen in his pictures. I'll come to this later, because I know I've got a picture of that later. I came up with a thing which is now referred to as a tribar. I'll speak about that later. But then I mentioned it to my father, and he then came up with staircases which went round and round and round. Neither of us nor Escher knew about the work of Oscar Reuterswärd, who was a Swedish artist who had played with things like this. And Escher didn't know about his existence, as we didn't. And he'd had things like this before we did. I'm not quite sure how many of them, but he certainly had some of them. And this was the kind of thing that the staircase, you see the monks, there are 2 sorts of them, one going one way around and the others, they're all going up all the time, and the other ones are going down all the time. And so this was based on a design that my father made out of the picture which I'll show you later, the tribar, which we'll come to. But anyway, my father wrote to Escher and described, we wrote a paper, my father and I did, and we gave credit to Escher and to the museum and sent a copy to him, and my father had a correspondence with Escher. But I'll talk about that later. And I'm going to say that this is an illustration of something, a nice idea in mathematics, which I'll come back to that shortly. Now here's the one which is based on the actual tribar I had, which is a thing called waterfall, which Escher made a bit later. And you can see there are actually, I think, 3 of these impossible triangles sitting in that. I'll come to that later. But you can see also these funny figures on the towers. And my colleague and I are trying to write lots about the detailed mathematics, which is involved not just in the impossibility in this picture, which does describe a kind of mathematics, which I'll say a little bit more about later. It's called cohomology. The pictures at the top are rather intriguing also, but let's not go into that. Curiously enough, Escher had done something himself in the meantime, which he made this picture called Belvedere. And this illustrates the same feature. You see the bottom part of the picture is perfectly consistent, and the top part of the picture is perfectly consistent. In the middle, you have an ambiguity. You can join things up one way or another, and Escher has chosen to join them up in a way which makes the bottom part inconsistent with the top part. And this is also an example of the same kind of notion. Locally, perfectly possible, but globally runs into an inconsistency. So I'll come back to that in a minute. So let me go forwards if I know how to do that here. Now you see, a little bit later, I was visiting Holland, and I was driving around and with my then wife, and I can't remember, I was getting close to a place called Apeldoorn, and I knew from my father's writings, communication with Escher, that Escher lived quite close in a place called Barn, which was not too far from Apeldoorn. And he also gave me Escher's telephone number. So I phoned up Escher, just out of the blue, and I said we've been traveling, and he invited us round to tea, which is very nice of him. So I came round to tea, and I think my wife and his wife chatted to each other, but I talked to Escher, and we sat but other end of a long table. There was a long, I don't know about as long as from here to those chairs out there. I was at one end, and he was at the other end. He had 2 piles of prints on 2 sides, and one on his left, he said, I don't have many of these left. And then the other one, he pushed towards me and said, choose one. So I thought, my gosh. Of course, all the famous ones were in the one he didn't have anything left. So I went through it, and finally, after great hesitation and difficulty, I chose this one, which is called Fish in Scales. And he was rather pleased that I chose this. He said, most people, he said, don't really appreciate that one. You see, this one is a sort of kind of violation of the theory of types or something. It's a logical paradox. And you see, look at the top right-hand side. You see a big eye of a fish. Then you move your way back along the back of the fish, and you see what were originally its scales become little tiny fish. And those little tiny fish become bigger and bigger and bigger until one of them becomes the one on the right. And you see a big eye looking right to the left now, sorry, on the left. And that big black fish looking to the left is one of the ones that came from the scales of the first fish. And its scales now become fish again, and one of those becomes the original big fish. So there's a sort of paradox in this picture, which, as I said, people usually get confused by the picture. And although I was confused by it, I wasn't quite as confused as I might have been. So he allowed me to take it with me, which I still have. I should say, it's no good burgling my house because it's not there. It's in the Ashmolean Museum at Oxford. It's possible to see. You have to get permission to look at it. It's not, I don't think, shown in normal. I have this, but I have also the one that my father was given, which was of the... Now, I want to show you something very similar, which this is a picture called Print Gallery, and this is very similar to that fish in a way. Those fish, I should say. I'm not sure how many there are. But anyway, this one, you see on the bottom left of the picture, I can't quite see what I'm looking at here, there's a little boy looking at a print gallery, and then as you follow the print gallery, it goes around, and you follow it all the way around, and you see finally that the boy is actually in the picture he's looking at. So it's a paradox of the same sort as the fish. As far as I'm aware, those are the only two illustrating that sort of paradox that Escher had. There's a little story about this, because in the middle of this picture, Escher sort of gave up and he put his signature in the middle. That's all right. But a couple of Dutch mathematicians decided they'll do something better. So they worked out, let's do a lot of complicated mathematics. How did Escher draw this picture? It's quite extraordinary. It's interesting because you can see some of Escher's sketching. And he claimed not to know any mathematics, which is quite extraordinary because he obviously had enormous mathematical skill, actually a geometrical skill. But he didn't. How did he work out these things? It's quite extraordinary. And the Dutch mathematicians worked out a formula for the function. It's a holomorphic function. It's a function, a complex function on the plane. And then you can see then how to fill in the gap. You put the whole picture in the gap, and then there's a little hole there, and then you put the whole picture in that. And then they made a movie of it. So you can look at this, and the picture gets bigger and bigger and bigger and bigger, and you can see the little thing in the middle gets bigger until it's got the size of this one, and then it grows in the middle, and it just goes on and on forever. It's pretty eerie. So you can see it's really a nice thing to see. But to work it out, and you can see how Escher did this, he had this sort of graph paper which with these functions. I think what he did, he had such a good eye that he could draw this graph paper with squares. So it was kind of like square paper with little small squares. And he knew that if you could change the size of the squares, but if you kept them looking like squares, then they were small squares, then that is a conformal map. And I suspect he did it just that way, rather than working out equations as the Dutch people did. So I don't know, I have no evidence, but you can see some of the workings out he had with these pictures, and he drew it out very, very accurately with the same sorts of curves, and he seemed to have done it by making sure that the little tiny squares really look like squares. So it makes it conformal, so that there's no squashing or stretching in the middle. If those squares remain squares, then it really is a conformal map. So I think that's how Escher did it, without actually writing down any equation. I'm guessing, because we don't really know. Okay, I hope you can see this. This is actually the picture in the article which seems evidently to have won a Nobel Prize, but it's on a paper I wrote in 1964. It was published in 1965. And it is a picture, a space-time picture. Well, you can't draw the dimensions, but it is a space-time picture of a collapse, gravitational collapse of spherically symmetrical material to the time is going up the picture, and the little cones is really what I want to talk about. Those little cones are these light cones or null cones, which I talked about before, and they tell you the most important part of the geometry. And as far as things like Maxwell's equations, they tell you all the geometry that you need to know. But if you've got matter fields as well, then it's not the whole story. But the problem is that when you have this thing I call a trapped surface in the middle, then you can't avoid getting singularities. So that's really what it was about. And these are the cones. So we have a time direction and 3 space dimensions, and those cones are just drawn as little ones. I'd like to draw pictures of things a little bit science fiction-y. I think I was writing a picture, that doesn't make sense, does it? Writing a paper, and I wanted to include something about extracting energy from a rotating black hole. And I realized you could do it by throwing particles in, and the particle divides into 2 and it comes out giving more energy. One part comes out, the other part goes into the hole, and the part coming out has more energy in it than the one that went in. And that's because the one that goes in effectively has negative energy, which you can do if you rotate. Well, it's a question of how fast you rotate with the black hole and all that stuff. I won't go into that. But it's correct. And I had an alarm. I'd done it this way in the paper, and then I thought, I'm not quite sure it's right. Do I know that that particle actually can get out again? And I hadn't calculated that. So I retracted that. I just eventually put it in a footnote and did it a different way. So this is just sort of playing with science fiction. And I imagine there's a black hole in the middle, and there's a civilization with these creatures who erected these structures which go around the black hole. And because of the way that energy and things called killing fields work, you can see that by lowering things into the black hole, the people in the inner ring can lower through, and they can extract energy, and then they can give the energy to the people on the outside. So I convinced myself you could extract energy out of a rotating black hole. Later on, I realized that the argument was correct, the original one, so I wrote a paper with a graduate student, that was Roger Floyd, and we did publish it that way. Anyway, let me continue with this. I'm talking about cosmology, and here is a picture of the universe according to standard cosmology now. Of course, I had to throw away a couple of dimensions, and I also don't know whether the universe is spatially open or closed. So you have to imagine it looks as though it's a bit closed because the spatial directions are going round horizontally, but instead of them closing up, it gets all wiggly, so they may go wiggling off forever. So my pictures tend to look that way so as not to bias whether or not the universe is spatially closed. So it might be spatially closed, it might not. But here I'm employing a trick, which is this conformal trick, which is really the Escher trick, as I said before, and I think that's what I'm saying in the next picture. No, I'm saying something slightly different, which I'll come to in a minute. What you can do is squash infinity down. I find this very useful to talk about electromagnetic radiation, gravitational radiation. Squash infinity down, like in the Escher picture, and then you can see what's going on to infinity. Infinity is really pretty well like anywhere else, and so you can do your calculations out there, and you can work out what energy looks like and what energy flux and things like that. And in those days, we thought the universe was asymptotically flat or something. We didn't know about what people call dark energy these days. We didn't know about the cosmological constant being positive. Well, knew but it could be, but the fact that it's actually there and being positive was not known at the time when we were playing with these things. But then it became known, and so I put it in. And if you put it in, you've got an infinity still there, but it's a nice space-like surface. It's very much like the Escher picture. You can squash infinity down, which is what I've done. So on the right-hand side, you see infinity squashed down. Now at the bottom, I've done the opposite trick. I've stretched out the Big Bang, which is really, in detail, an idea to a graduate student of mine, Paul Todd, who later became a professor at Oxford. Now he's retired. I realize I'm getting old when my graduate students have retired from their professorships. But still, anyway, he really explored and had the idea of doing the opposite trick, of stretching out the Big Bang. And then the condition on the Big Bang, you see, there's something very funny about the Big Bang. I could go and tell you a long story about that. But the Big Bang is very strange. It's not a generic thing at all. It's something where all the gravitational degrees of freedom seem to, for some reason, be not there in the very early universe. Why are they not there? Well, the idea was, not why, but how do you describe it? So Paul's idea was to say, okay, you say that you continue the Big Bang to something before it. And this is sort of illustrated by Escher. I'm trying to find an appropriate Escher. It's not quite right, but it's sort of doing it. So you see, Escher is sort of doing the opposite. You're going into the middle, which is like where the Big Bang is, and it's as though you could stretch that out. I could never quite find an Escher picture which did it more than this. There are others which perhaps a bit more than this one does. But he's sort of doing the same kind of trick. You're looking at the middle, which you might think of as being a singularity, and you're making it look quite harmless because it's just like everywhere else. So that's the sort of thing Escher is doing there. Now, here we are back at this picture. There's nothing wrong with this picture. I don't know how many cosmologists would like to use it, but there's nothing outrageous about that picture. Nothing outrageous. What is outrageous is that. What I'm saying is that the Big Bang, not just as Paul had suggested, is nice and smooth when you stretch it out, but really is the continuation of the remote future of a previous, what I'm calling eon. So I'm calling our Big Bang to our remote future our eon. There was an eon prior to ours, which had its remote future. That gets squashed down. Its infinity became our Big Bang. Okay, people have a lot of trouble taking this seriously. You have to have one thing to make it take it seriously. That is, the matter shouldn't know how big things are. That would be the case if you have matter without mass, because mass is the thing which determines the scale. I'm not sure whether I've got that. I think I've leapt onto something else, but let me just say that for the moment. If you have no mass, then you don't know the scale. If you have Maxwell's equations, which is the equations governing light, electromagnetic fields, or even in quantum mechanics, it's the equations governing the wave functions, if you like, in quantum mechanics, that doesn't know big from small. And so, in a sense, if it was just photons in the remote future, then this picture would be a pretty good picture. It's not just photons, so you've got to worry a bit more than that. I'm not going to worry about what the worry that you have to have, but I think one can deal with that worry, but it's more questionable. But the general idea is that it's mostly photons, so maybe you can get away with it. The Big Bang, it's the opposite sort of argument. It's very, very dense, instead of being very rarefied, but when you stretch out dense, you get rarefied, so that works. It's very, very hot in near the Big Bang, and that's the main point. It's so hot that particles are moving around so fast that the mass becomes irrelevant. Its energy in its motion completely swamps its mass, and therefore it can, in effect, be thought of as being without mass, and therefore doesn't know big from small. So that's the sort of motivation. Of course, that's the sort of waving hand argument, and you might argue against it, quite right. But nevertheless, this is the picture. I want to go back now and talk about things which perhaps I should have put earlier in my slides. This one. This is the sort of picture I came away from Escher after the conference in the Netherlands that I'd been to in Amsterdam, and shown a picture like this, although not with as much perspective. I'm showing you can have a tri-bar with a lot of perspective. It still works. People tend not to draw it with perspective, but it still works with a lot of... Escher put perspective in his pictures, not as quite as brutally as in this picture here, but you can do that, and you get paradoxes with that, which is sort of goes along with the cohomology paradox. Why do I say cohomology? You see, the idea is you could imagine building a thing like this out of little blocks, corners, say, and you have rules about how you glue them together. So you get your list of constructors, how to build a corner. Another one, so how to build a corner, how to build a corner. And then it says how to glue this one to this one. And then it says how to glue this and this. There's a rule that's got to be true if you can make the thing in 3 dimensions. If you can't make it in 3 dimensions, there's a thing called cohomology, which tells you sort of how far off it is to make it. It turns out that the Maxwell equations can be described in twistor theory. I haven't told you about that, but it's quite interesting because there's a little story here, because I think, yeah, it was really funny. I was being interviewed by some people who want to make a film about twistors, all things. I mean, the interviewer was more interested than the physicists were in the subject. And they wanted to know, they'd been making these films for a long time. And then at one point they said, what are twistors good for? I thought it was a bit late asking me that question. So I said, well, you can use them to solve Maxwell's equations. Maxwell's equations tell you how electromagnetic, how radio waves work and all that. Electricity and magnetism and radio waves and light. So they say, oh, how does that work? Oh, well, it depends on an idea I couldn't possibly explain to you. What's that idea? Oh, this idea, it's called cohomology. I couldn't possibly explain that to you. I said, oh, no, we'll try it. No, there's no way I can explain it. So I got home and I thought, yes, I could. It's this. This is a description of cohomology. Of course, they didn't use it. But still, that was sort of the origin of how to think about things in twistor theory. I'm not talking about that, so don't worry about it. But this does illustrate that you can put the perspective in perfectly well. And here is showing you, my father made this picture at the bottom, showing you the dogs. He found, the joke was, he found, I think in a toy shop, that you could get these dogs which were identical except they were different sizes. And so the idea was you put them in the staircase. There is a break in the staircase, but that's disguised because just at that point the dogs change from small to big. So it looks as though where the break is, there isn't a break. Also, I think the little hind legs are glued to one of the things. I can't remember exactly. So it's really very hard to see where the break is in the staircase. And only when it gets round to the front, you see these dogs looking at each other with completely different sizes and say, how could that happen? So the fact that the sizes are inconsistent when you have perspective was an interesting feature of this cohomology. The top was a picture I drew, which is illustrating this rather stream situation where the little baby is playing with a toy train and the little figures. And they climb down and then they climb up a ladder and then they become the same size and then so on. So it's a contradiction of scales, which is illustrated in this picture. Just like the dog, so it's the same thing. Am I at the end? I'm not sure. No, this is the Escher picture, which we had before, illustrating the staircase going round. But he doesn't emphasize the scale feature and the fact that the monks going one way around will get smaller and smaller, and the monks going the other way around will get bigger and bigger. But that was the thing. I want to end by showing you a couple of things. This one in particular, I was at a conference in honor of Escher, and I was going to give my talk the next day. And I said, it was an American mathematician who talked to me. He said, oh, what are you going to talk about? I said, well, I might try and illustrate how Escher's pictures talk about cohomology. And he said, and I showed him this idea. And he said, oh, can you use that for any other group? And I said, I have no idea. So what about Z2, or Z2 as we say? And I thought, gosh, you can do that too. So eventually, not at that conference, I had a picture at the conference, but I didn't have these pictures there. These are steps and things. I showed these two, or one of them, to an Escher expert, and I was saying, look, can you see what's wrong with this picture? No. Could you make that thing out of wood? Yeah, I don't see why not. Yes, could you really? Yeah. Have a go. Well, you see, you can walk up the steps one side, and you walk around the back, and you can climb down the steps to the other side, or whatever it is. And when you get back to the beginning, you thought what were steps were the other way around, so it doesn't make sense. It is an illustration of cohomology, but using a different group. It's the Z2 group. And there are two ways of doing it, one with a 7-fold thing on the right-hand side and a 5-fold thing on the left-hand side. So I rather like doing it to illustrate something that Escher would have loved to see if he'd lived, but unfortunately. We almost did this, actually. I don't think I've got a picture of that doing it, but he did have examples of what you might call relative cohomology, using the Z2 group. Yes, he did do that. Here's something which Escher did. This is just some pictures of what Escher didn't do. Here is when I'm sure he would have done wonderful things. These are kites and darts at the bottom. You have an infinite number of kites and an infinite number of darts with little notches and knobs to see how you must fit them together. And the only way you can do it is by having a pattern which never repeats itself. And you've got this at the front of the college, haven't you, one of these things? Yes. But they're not birds. You see, I was trying to Escherize them by these bird creatures. Escher would have done wonderful things with these things, but unfortunately, I was just too slow. I should have thought of this a couple of years earlier, and then he would have done it. Escher and my father died about the same time, so they never saw it. I'll end with this, which is an invisible, impossible object. So you have to look at where is the tribar. It's invisible. Okay, thank you very much. I should come over there for questions.
So thank you, Roger, so much for that inspiring talk. I mean, what struck me was that you only showed pictures throughout this, but the talk was about maths and about science, and it all came across. You know, so about quantum mechanics, the Big Bang, black holes, but there was no maths, and we could visualize it through these amazing pictures. Okay, so I now would invite, if Roger's happy with this, for questions.
Sure.
You happy? And a couple of you will bring the microphones around. Please wait till the microphone arrives because this lecture is being recorded and we'd like to record the questions and answers. And so please wait. So who would like to ask something? Please, in the corner. So just wait a second for that.
Thank you very much for the talk. It was really interesting, and I was quite intrigued by the photo. I mean, the image of the black hole, because and then extracting energy. Because I'm doing an internship about nuclear fusion this summer, so I'm quite interested in physics and energy extraction. Mm-hmm. So would making artificial black hole something would be a post-nuclear fusion era research or something, or would you think there is something else which is going to happen after nuclear fusion?
So I missed what the question was just.
What's going to happen after post-nuclear fusion power generation or something?
I see. Well, of course, the people extracting energy were keeping well on the outside. Well, they have to drop things in, of course, because you don't gain any energy unless you drop something which is in effect of negative energy. And what you're really doing is you're not really violating energy conservation because you're using the rotational energy of the black hole. So all the time you're slowing it down. But that doesn't address the question of what's going on inside the black hole, which doesn't touch really. And I'm not sure if your question related to what's going on inside. You see, as I mentioned in the talk here, sometimes, people I know in Oxford complain that I got the Nobel Prize for the wrong thing. That is to say, the citation said the Nobel Prize was for proving, or something like that, that black holes were a robust prediction of general relativity. Whereas what I actually showed, in a certain sense, was that singularities are a robust prediction of general relativity. And I do remember struggling away for a long, long time, trying to see, there's a thing I labeled cosmic censorship. You see, it's somehow naked singularities are things you're trying to prevent, and they're kind of wrong. You shouldn't have naked singularities, so that you have censorship of the singularities, and the good Lord is censoring you from seeing these naked singularities. And for a long time, I don't know, I was really more open-minded, I think, about the existence of naked singularities than most people were in the area. And I think it just seemed to me you needed a proof. I mean, you can have explicit solutions with naked singularities. They can certainly exist. It's just they're not stable. So the question is more, in the generic situation, do you get naked singularities? So I postulated this cosmic censorship, which is that naked singularities do not occur generically. Now, it's still not clear, even from the mathematics, whether you could have a generic type of singularity which was visible from the outside. I don't think so. I mean, I've come round completely to thinking that, yes, it's black holes are the right answer. But I think if you'd asked me, I don't know how long ago now, when I was actively thinking about those things, I would really more have been a don't know on that one. So your question isn't being addressed, I think, by what I've said. But I can't say anything about what's going on inside, except that I used to think like everybody else at the time, everybody, I mean, working in this area, that the answer to these questions is quantum gravity, that we have to have a theory of quantum gravity to understand the singularities in general relativity. That's not so much my view now. It's certainly true that the singularities in black holes, you're going to get that, and you're going to get to situations where the curvatures become of the nature where you're going to have to use quantized gravity. But what you're not doing in that thing is gravitating quantum mechanics, which is what I really think you need to do. So the effect of gravitation on quantum mechanics is not an activity that many people study, but I think that's something one needs to look at more, because the quantum gravity doesn't answer the Big Bang question. It doesn't tell you why the singularity in the Big Bang is so utterly different from the singularities in black holes. So anyway,
maybe someone else.
Sorry, I went on rambling.
Thank you very much. Thank you.
So maybe someone else. Another question. Yes, please. Yes.
Firstly, once again, about energy extraction. So we had this exercise that I wasn't quite convinced about. Can you use the Penrose process in a spherically symmetric Reisner-Nordstrom black hole with positive electric charge and zero magnetic charge?
Yes, well, as long as it is a black hole. I think so. No, certainly people have looked at that case. Certainly within some range of parameters you can. Yes. Of course, in the actual universe, the Reisner-Nordstrom black holes are not expected, at least you might have a little charge, but to have one which is other than a perturbation on the black hole. But there is a good question as to whether this process is in effect, in some form, responsible for the energies of quasars. You see, the whole subject, from my own point of view, came about because of the quasars. And that was, and people were seeing these spots in the sky, well, seeing in the sense of radio waves, these spots in the skies which were emitting enormous amounts of energy. And the amounts of energy and also the variation, they must be very distant because of the redshift, unless the redshift was gravitational, in which case it's worse. So it must be the distance, or if it's that, and therefore the energy must be enormous, vastly more than an entire galaxy's emission, and nevertheless you get variations in the intensity. So they must be pretty small, and by small I mean less than the solar system, and people began to think of things comparable with their short radius, in other words, what we now call black holes. And so the question was, is this original picture of collapse, the Oppenheimer-Snyder picture, where the dust or the material simply falls in towards the center and forms what we now call a black hole, is that realistic? Or does it come swirling round and come swishing out and produce all sorts of energy in that form? And that was a view, I think, that people had more commonly than the black hole picture. Definitely, yes. When I say more commonly, that's true, because I used to lecture at these conferences on relativistic astrophysics, and I could see disbelieving black holes, disbelieving, and then it got more and more and more. And when it reached about 50%, when it zapped over, more people believing in them. So it was quite interesting to see how the general point of view shifted over the years. But normally people didn't. But Reisner-Nordstrom, I don't think is that different. As long as the charge isn't too big, as long as you have a horizon rather than a naked singularity, I think it's very similar. But don't quote me on that, because I can't remember the details on it.
May I ask a sort of more general question
Yes.
about your, in your early work, your PhD work and your fellowship dissertation and what you did on algebraic geometry, that had almost no diagrams at all. I looked in your volume 1, collected works.
I wouldn't look
Your
at
work
this.
on algebraic geometry had no single diagram. There's long thesis and a second one. Were you inspired to move from pure geometry into mathematical physics because that was a better arena for your visual insight?
That's a good question. But let me tell you a little bit of a story there. You see, my supervisor originally was Hodge. And I used to see him weekly occasions, and he asked me, what have you been doing? And then I'd be doing this or that. And he said, very interesting, and then I go away and do something else. And then I came away, and there were usually rather long silences when I was talking to him. And I think I, at one point, did confess that I was using diagrams. You see, the problem, there were about 5 problems, the only one I properly understood was this thing about Cayley forms, which I did understand. And I could see what the problem was, and I thought I'd have a go at that one. And it was really going to his lectures, which were sort of sprawled. I mean, actually, they were rather good lectures. Don't get the wrong impression. They were good lectures, but you were hopeless if you want to take notes, because the equations were sprawled over the board and indices all over the place. And it was really to cope with his lectures, which I developed this notation where you drew little lines joining where the indices were up. And it was a way to tackle this problem. You really had to draw pictures. It was hopeless to just draw the indices. So it was to make the calculations for this problem make sense. Now, at one point, I confessed to him that I actually had this notation to draw little diagrams. And he said, very interesting, very interesting. And he suggested that I would write something up and show it to him. So we're all getting very excited. So, this is my opportunity. And I wrote out a really long screed about this stuff. And I gave it to him. And I think he got stuck on it. I don't think he went through very much of it. And I think not long after that, he suggested that Dr. Todd would be better to be supervisor. Actually, he thought that there was a mistake in my I didn't realize that until almost 3 years later. He thought I'd made a mistake in my calculation. And it was only when he came up and he and Todd had talked about it and finally repeated one of these calculations. And he came up to me and he said, you were right all the time.
Very good.
But I think that was part of the reason he got rid of me.
I think we better bring this to a close. Thank you very much for the reception. So let me just say that if you've been inspired by this talk, all you have to do is to go to the St. John's College Library. So first of all, you walk across a Penrose tiling, which you've probably seen. And then I recommend also you go down to the basement where you'll find, it's 7 volumes of Roger's collected works. I've got the first volume, which, by the way, has some of the highlights. But I will return it shortly. And you will be able to consult all the volumes. And you will be inspired by the wonderful pictures, some of which you've seen today, some not. And so many of Roger's papers have wonderful figures in. It's really lovely to look at. Starting with the tribar, there's a couple of papers which Roger wrote with his father. Then some puzzles for the Archimedean magazine, I think. And later, most important pictures of this cosmic collapse, the collapse to the black holes or to the Big Bang. So do follow up on this talk if you found it interesting, which I'm sure many of you will have.
Can I add one word of advice?
Yeah.
Don't look at my PhD thesis. It's dreadful. I had all the wrong notation, and the way of translating diagrams into notation, I chose the wrong thing. I claim I can do it now much better, so you can look at later papers, that's all right.
Okay.
But
So
the
you've got a choice of papers to look at.
Don't look. You can look at my fellowship thesis. That's
The fellowship thesis is recommended, but not the PhD. Okay, let's thank Roger again for a wonderful talk.